Okay, so let's continue the second part of the randomized control trial. So I will be focusing on the data analysis and the interpretation. Generally speaking, there are two stages of the data analysis. The first one is so-called analysis of baseline data, because we did the baseline measurement, right? We did it for a certain purpose. We did not do it for nothing, right? And the second part is to perform the outcome comparisons. And both of them, we have certain purpose of it. The analysis of baseline data is basically, there are two major points. The first one is to assess the similarity of groups formed by random assignment. That's the most important thing about randomized control trial, because we perform the random allocation. So theoretically, everything about the two comparison groups should be very similar or even the same to each other, right? So we need to check it out to see if it really works. So that's the second point. We have to detect possible tampering with the randomization process. Because we did it randomly, it could still happen by chance that there's some imbalance in certain variables. So we have to detect it, and then we could control it as an uncontrolled or not fully controlled confounder at the second stage. Okay, so we need to detect the confounder which is not 100% addressed by the process of randomization. They are linking to each other. First of all, we have to check that if it really works for the randomization. And the second bit is so-called outcome comparison. And there is a special skill called intention to treat analysis. But don't be scared by the name. It's not about a new statistical method you have never learned before. It's just a way to perform the data analysis. Okay, we keep it intact. So everybody just stay in their own group, no matter they are in an intervention group or in the placebo group. So intent to treat analysis is a way to perform the analysis. It's not really a new statistical method, so you have to keep that in mind. But you need to know why we need to use such a weird way to perform the final outcome comparison in the end of the data analysis. Okay, and last bit that it's kind of optional. You could do it or not. You could perform the treatment actually received or not. But this is essential, 100%. Okay, and baseline comparison is essential, but this is optimal. I'll tell you why bit by bit. So don't worry. What is so-called intention to treat analysis? Basically, we just keep the groups formed by randomization intact for comparisons. If you have a lot of experiences for the practice of randomized control trial, it's very unlikely that you could keep every single one from the beginning to the end, right? So people might leave without telling you any reason, right? Or people just tell you, I don't want to do it anymore, no matter they are in an intervention group or in a placebo group. Okay, but you cannot tell them that if you are not coming, we will stop paying you. Okay, or you will get any punishment or anything. That's the consideration. That's the concern for ethical aspects. You cannot do anything against them, but you can still pay them to come back to provide their outcome measurements. Okay. That's so-called intent to treat analysis. Without the data, you cannot do anything, right? But if they start doing the intervention or they start doing the placebo, that's fine. They just come back to provide the final information for the outcome measurements. Then you could have the data for the purpose of intention to treat analysis. I'll tell you why it does matter and why it's so important to do that. Because intention to treat analysis could preserve the substantial benefits of randomization. Or we could say that we could avoid the possibility of selective missing because of the side effect or because of the bitter taste of the medication or the uncomfortable side effect because of the intervention. Or maybe just in his or her imagination or so-called placebo effect, psychological effect, right? Or it could be inconvenience for the participation of your research. Okay, but you are going to give them incentive to come back again and again and again, right? But it's very important to keep them in those groups because you've done randomization, right? If they left without telling anything, they lost the information, there will be a potential source of selection bias. That would be the worst scenario. Okay, so the best strategy to deal with or cope with selection bias is to avoid it, right? So this is the first bit. We have to avoid the possibility or minimize the possibility of any concern for selection bias. And also keep the substantial benefit for randomization. It's 100% be the preferred comparison to avoid selection bias. I'll repeat it. And the other thing is that you'll be almost always be able to underestimate the true effect or the shifting to now. You might think that, is this good? Yes. If the treatment effect is this big, but some people stop doing it, I mean, in the placebo group, and the effect might be a little bit lower, right? Or in a placebo group, people might start to take it for some purpose. Maybe he or she got headache or pain, and he or she has no choice to take the medication for intervention, maybe painkiller. So they are closer to each other, right? But if the outcome is still significant, then the real effect should be even bigger, right? So this is what we want. We want to see something significant, but actually be more likely to be underestimated. Then the real effect of intervention will be even stronger. Okay, that's the idea that why we need to do it with the intention to treat analysis. Okay, in terms of epidemiology, we call it the shifting to now or shifting to no differences. Okay, so this is very important. About the treatment actually received is not essential, but it will be very useful to adjunct to intention to treat analysis in understanding why intervention did or did not differ. Okay, for some studies, they did it, or they might put it in a supplementary table, not essentially in the final results, but it could be put in the supplementary tables. And it could be influenced by dropout, crossover, and non-compliance. Then it becomes something like a non-experimental comparison. So if you find something different, I mean the outcome from intention to treat analysis is very different from treatment actually received, then how can we make the conclusion? We still prefer, we trust more about the intention to treat analysis. This is just for reference only. Okay? But the best scenario is that both of them show exactly the same outcome for data analysis. Okay? So this is so-called intention to treat analysis. Very, very important. Or you can perform a subgroup analysis to detect the effect of intervention in relation to subject characteristics. We call it, remember in the class in the confounding and effect modification, we call it effect modification, right? So maybe the medication doesn't work for female, but work for male, right? That is a perfect situation for effect modification. Or the other example is gene-environment interaction. The effect of the exposure from the environment could be modified by the genetic characteristics. Okay, so that's the purpose of subgroup analysis. But the problem is that if your sample size is not big enough, subgroup analysis might end up to show non-significant because of the limited statistical power. Okay, and the more you do for subgroup analysis, is more likely to detect a significance which does not really exist. This is so-called the multiple comparison problem. So you could do thousands of different kind of tests. You could always find hundreds of significance, right? But it's alpha error. Alpha error is the necessary evil in statistics, which is fixed at 5%. Right? So in other words, if you just do the statistical analysis randomly, you could always find 5% of tests that show significance, which only happen by chance. Simply by chance, there's no correlation at all. Okay? But if you do many, you get many significance, which does not make sense. That's why we have to have established a hypothesis which makes sense. Okay? We have some ideas to make sure that it's likely to be a correlation. And then we start to design a study, perform the study, and do the statistical analysis. That's the whole process. We don't do it blindly. We have the hypothesis in mind. Okay, so subgroup analysis cannot be abused because of the issue of multiple comparison problem. Okay, and also it could decrease statistical power because subgroup, so it's smaller and smaller and smaller. Again, this is not essential, but be very helpful for us to identify a group of people who got a stronger response to the intervention, right? Maybe generally speaking, in a whole, it doesn't matter. I mean, there's no effect detected by the study. But maybe in a smaller group, it works there, right? And there are two terms. The first one is efficacy. The second one is effectiveness. If you check the dictionary, you'll find out they mean very similarly, right? But actually, there are some subtle differences in terms of epidemiology, although it's very likely to be mixed up in the title of the journal articles. But you need to know the real meaning behind it, right? Efficacy means that the extent to which a specific intervention, procedure, regimen, or service produce a beneficial result under ideal conditions. So this is something you could find with a perfectly conducted randomized controlled trial. No one running in, no one running out. No one drop in, no one drop out. And everyone follow the protocol in details, and the randomization work very well. And there's no information bias, selection bias, blah, blah, blah. Then it's efficacy. Okay? But is it possible, available? Maybe not, right? But that's the ideal target we are going to achieve, right? So effectiveness will be something in more real world or in reality. So effectiveness means the extent to which a specific intervention, procedure, regimen, or service when deployed in the field. The field could be community, or could be hospital or clinical setting, right? That's what it is intended to do for a defined population. So this is more like a real world thing. So if you perform a study with a study design randomized controlled trial, in the title, which one should be preferred? Effectiveness should be preferred. But sometimes you see people put efficacy in the title too. In the title, we prefer to use effectiveness because that's the reality happening in the real research in the field. And efficacy is generally talking about something happened in an ideal situation. Yeah, but sometimes people mix it up. This is the goal we want to pursue, and this is actually what we get. I want to be the most handsome, richest man in the world, but I'm Chin-Kuo Chang. If we use efficacy, and please use from the beginning to the end in your article. Don't say efficacy some place in your article and some place called effectiveness. That will be even more confusing. Okay? But if I were you, I would suggest to use effectiveness from the beginning to the end to make it consistent and telling people that that's what we really found in our research. Okay? But in discussion, you could talk about efficacy because you are trying to identify the efficacy in a perfect situation. That's the goal, right? Or just the difference about the term, which is kindly confused or misused in articles. Yeah. But there's no 100% or very clear cutoff point. Or this is efficacy, or this is effectiveness. But we are talking about the true impact of the intervention. Okay? So efficacy will be something that happening in an ideal situation in all the population in the world. But it might differ in the local population, right? Ethnicity background or younger, older age, right? Or people are from different socioeconomic background, something like that. So it varies, right? But the efficacy should be only one. Something exists in there, like a paradise. But in the calculation, that's the other term. Efficacy, which means the reduction in risk. So this is a term in statistics. When I'm talking about efficacy calculation, in biostatistics, it's defined like this. It's rate in those who receive placebo, subtract rate in those who receive the vaccine. So this is in the situation of the protection. Give them vaccine is to protect them from the disease, right? Divided by the rates for those who receive the placebo. Okay, so what's the meaning behind it? It's the percentage of the people who are protected because of the intervention of vaccine, right? It's because this high, right? And because of vaccination becomes this low, right? And what's the percentage protected by the vaccination? Okay, it's called efficacy. This is the statistic. And the other one is the so-called NNT, number of patients who would need to be treated. It's called NNT, such a long name. But it's very straightforward. It's very straightforward because the meaning behind it is very straightforward, which is defined as 1 divided by rate in untreated group, subtract the rate in treated group. Okay? It's a long name with a long formation. But the meaning behind it is very straightforward. Is that how many people you treated, you could save 1. Right? So if you want to provide a public health intervention like vaccination, then you could, to avoid death from COVID-19, for example, then you do the calculation of NNT for death. Then you could tell the policymaker or the president that if you give the vaccination to 100 people, you could save 1 death from it. If the rate here is mortality, then it's the lives saved. If this is the probability of getting sick, then just keep them, how many people need to treat to protect 1 person from getting sick. I'll show you more examples, then you will realize what is meaning, what's the meaning behind it. The formula is a little bit messy and stupid, but the way to explain it is very straightforward because the policymakers are generally simple-minded. They are very busy and they are, I don't know, but it's very easy to convince them with a simple number. Give them a number, they say, "Oh, I realize it," but actually they don't really understand it. Okay, exercise. After the exercise, I do believe that you will understand it. Okay, so here's an example in one of the top journal in cardiology called the Circulation. You could check the impact factor of the journal, Circulation, 20-something or 30-something, I can tell you. It's called Enhancing Cardiac Rehabilitation with Stress Management. That's important, right? Stress management might be able to protect people from getting heart disease again, right? It's kind of the so-called stress management training, a randomized clinical efficacy trial. See, it's called efficacy. But actually what they could get is effectiveness only, right? But in title, some people like to say, oh, we are going to do efficacy, which is not true. Personally, I prefer to use the effectiveness. I always say, oh, the effectiveness of our intervention or our treatment is like this and that. And use the term from the beginning to the end. But it happened. The information given in the abstract will be available for us to do the calculation for the efficacy and the NNT. Okay, so let's go through the abstract together. Okay, abstract. Background. Generally speaking, in background, we'll give some background information about why this does matter. Cardiac rehabilitation is the standard of care for patients with coronary heart disease. Okay, so after the heart attack caused by coronary heart disease, people would do cardiac rehabilitation. So it's kind of a standard way for treatment after the acute stage treatment. Despite considerable epidemiologic evidence that high stress is associated with worse health outcomes, stress management training, or called SMT, is not included routinely as a compound of CR, which is cardiac rehabilitation. Okay, so CR is traditional method, and SMT is kind of a new method. Okay, so it's pretty clear. Methods and results. 151 outpatients with coronary heart disease who were 36 to 84 years of age were randomized. So it's an essential component for any randomized controlled trial, right? To 12 weeks of comprehensive CR or comprehensive CR combined with SMT with assessment of stress and coronary heart disease biomarkers obtained before and after treatment. So what's the purpose for these measurements? Baseline comparison, right? We want to make sure that there's no differences between these comparison groups at all before we could start to do the intervention, right? A matched sample of CR eligible patients who did not receive CR made up the no CR comparison group. See? They find a third one. So now we have 3 groups. The third one is a group of people who matched to the CR eligible patients, but they did not receive it. They might refuse to take it. So that's why they need to do the matching to minimize the issue of confounders. All participants were followed up for up to 5.3 years, which is very long. And the median was 3.2 years for clinical events. Patients randomized to CR plus SMT exhibited greater reduction in composite stress level compared with those randomized to CR alone. The p-value is 0.022, which is significant. An effect that was driven primarily by improvements in anxiety, distress, and perceived stress. Okay, it makes sense, right? Because they give them some kind of the stress management training. Just calm down and deep breath and think about you are running in nature or swimming with dolphins, something like that. Just relax. Both the CR group achieved significant and comparable improvement in coronary heart disease biomarkers. And participants in the CR plus SMT group exhibited lower rates of, see, they call rates. Hello. They call it rates here. It's the probability of getting the disease of clinical events compared with those in the CR alone group. See, 18% versus 33%. See, so it's probability, but they call it the rates. It's simply that just the possibility got the cardiac event. Hazard ratio 0.45, 95% confidence interval, blah, blah, blah. And both the CR groups had the lower event rates compared to the no CR group, 74%. Okay, so I put all of the information on the whiteboard there. The intervention period were 12 weeks, right? And in this group, traditional treatment, CR, and new method, 18%. And the group with only traditional or regular care is 33%. So this is much lower, right? Pretty low. Okay. But the ones who don't even, or they even refuse to do the CR, but they have to be matching to this group, 47%. So pretty high and all significant, right? So that's the essential information about the outcome. So actually we got all the information available for the calculation for the efficacy. Okay, so the first one, practice, could you prepare your paper? The efficacy of CR plus SMT compared to CR is 33%, right? That's 33%. This, minus 18% here, divided by 33%, so 0.45. In other words, it could just saved almost half of the event because of the additive new treatment for SMT, right? It could save half of the events, right? It's much more straightforward than showing you the 80%, 33%. Almost half of them could be prevented. So it's kind of secondary prevention from the clinical events. Okay, and the NT will be 1 divided by 33, subtract 18%, so 6.67. So in other words, if you apply the new method, this plus this, and comparing to the old method, you just need to treat a little bit higher than 6 people, maybe 7 people. You can save 1 from the unwanted event in the follow-up period. Okay, you can save 1. So if the number is smaller, then that's better. So if the number is 1, which means that whenever you treat anyone, everyone works, right? If the number is huge, 1 million, then you need to use the new method to treat 1 million people to save 1, right? So it's not a good one. So these two information just show us some simple idea that how the new treatment is better. Okay, so the higher the better for this one, right? 1 would be the best, right? And this is the lower the better, but 1 would be the best. So every single one you treat it, then he or she will be saved. He or she will never ever be able to get the event afterwards. Okay, so single number, Remember, everything in epidemiology, we are trying to make something, try to find something very succinct and simple, like relative risk, right? It's a simple number. Standardized incidence ratio, SIR, a single number, right? SMR, single number. And now, single number, right? So it will be very helpful for you and straightforward, intuitive, to help the stupid policymaker to make their own decision, to support your research or apply this kind of intervention, become a regular treatment methods. Okay, so let's try the other combination, like CR to non-CR. So let's compare the traditional method to the ones who refuse to take the traditional method. CR vs no CR. So what do you see? So, right? So you just need to replace one number. Okay, so this is very straightforward, right? No?
You need to use 33.
Oh, sorry. Yeah. Anyway. Okay, I'll give you 2 minutes. NT, so it's the same. CR versus no CR. Some people don't trust the traditional routine methods. Then we could tell him or her that if you don't do it, then something will happen. I can show you that in a randomized controlled trial, how many % of people could be saved because of the traditional method, right? If someone refuses to take the CR, which is a routine method, you could tell him that there's a randomized controlled trial published in the top journal circulation. It showed that how many % of people could be saved because of the traditional methods, right? If he or she refuses to do it. Okay? It's very straightforward. But the single number is easier to understand for everyone, right? Rather than show them those numbers or even such a huge portion of numbers, of words. So is that more straightforward? I don't think so. Is that straightforward? Maybe not. This is straightforward, intuitive, informative. Yeah. So the answer would be 0.3. Okay, so it's the answer would be 7.14. Okay, so now the key point is how to explain it to the patient. So that if he refuses to do the treatment, you can tell him that if you do it, you could save 30% of the possibility to get the cardiovascular event, or clinical events, which is defined clearly in the article. Or maybe the next coronary artery disease, or AMI, or stroke, blah, 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 is other cardiovascular diseases. Okay, so 0.34, 0.3. Okay, so comparing to the one without any treatment after the acute stage of coronary heart disease, every 7 people you treat them with the traditional method, you could save 1 from getting the event. Okay, afterwards. Does make sense. Okay, the third one is the new method compared to the one who refused to take any treatment. So this CR plus SMT, right? It's CR plus SMT. I could do the calculation. Stress management training. Yeah. It should be simply deep breath. Think about your grandma, or maybe it's not a good one. Think about your first girlfriend, something like that. Or thinking about lying on the ocean, floating, right? Or count 1, 2, 3, 4, 5 to 10 before you do anything, right? Something like that. I don't know actually. Yeah, but it works. According to the information, it works. Okay, so I have 2 minutes to work on this. Yeah, the key point is not only using the formula, it's also important to explain it correctly. Okay? Okay, 2 minutes. I'll keep quiet to give you 2 minutes to think, to comprehend what it's for. But even if I don't do it, I can imagine that the proportion will be much higher, right? And the number will be much lower, right? Because this traditional method plus new method compared to doing nothing, right? %62%, and the NT will be 3.45. See, like what I expect. This number will be bigger than the previous two, right? And the number will be smaller. So every 3 to 4 people, you could save 1 from the event after the, okay. So let's keep on moving. I just give you that there are a lot of more modification for randomized controlled trial, but still very effective. Okay, so these are just examples, so don't worry, okay? So there's another randomized controlled trial modification called the parallel RCT, or crossover or step wedge design. So this is so-called parallel. This is more possibly happen in the situation of the launch a new policy. Because it's not possible that if you apply a policy in the community, every single one should be served, right? So you cannot say, you can enjoy the new service, but you don't, right? So the only thing we can do is just, it could be happened by county or by province, but it cannot be possible to do it individual level. So this is so-called the parallel method to apply the intervention. But it can still do the randomization, right? So the city 1, city 2, or county 1, county 2 will randomly assign to a new policy, okay? And city 3 and 4 just randomly assign to the old policy, okay? Then we could do, that is so-called parallel. Or they could cross over, but not always feasible, right? If you give them some new services, and it's very difficult to take it away, right? So the other possibility is that, so in the very beginning, the 4 city or county were not on a new policy. And then we decide that the order to join the policy randomly. This is called a step-wedged randomized controlled trial. This would be the most feasible way to do it for the application of a new policy. And it still works like a regular randomized controlled trial. This will make it very feasible, especially for the big scale and a lot of the, you have decided to do it. But what you know is efficacy, right? But in this kind of the studies, you will know the effectiveness. If you push, if you apply such kind of new policy to the community, to the whole country, then what will happen? Then what you can get is effectiveness, right? And the study design, a step-wedge design of a randomized controlled trial is a pragmatic design to deal with issues of repeat cluster assessment for policy research, or so-called policy rollout. So people and the community or county, the big unit, geographic unit is rolling in one by one with a random order. So it's also called the policy rollout. And sometimes clusters could only go from old policy to new policy, right? If you give them vaccination, you cannot take it away. So the crossover study design doesn't work, right? But step-wedge design will be possible if there is something like a vaccination. It could save a lot of the research implementation cost because since you want to, the application of the, since the new policy is almost 100% confirmed that you're going to do it, then you could do it like a randomized controlled trial. Even a good idea from a statistical perspective. People might think that, is that still a randomized controlled trial? Yes. And in terms of biostatistics, it's even stronger. Or you can even provide a better statistical power. There are some statisticians called Hemming. They prove it the statistical power is even higher. See, a typical randomized control trial power is 50%, but SWD, this kind of study design could be as high as 82%, which is even better than a traditional randomized control trial with allocation or randomization at individual level. So it's saving time and money, and even better in terms of methodology. Okay, but how it works? So gradually, we implements the new policy for each cluster, but assess cluster repeatedly before and after implementation of the new policy. Because they could do before and after study design, before and after intervention, or also you could do the comparison across the communities or clusters. And the order is the way we perform with the randomization. Okay, so the cluster that join the study in a random way. Okay, so it's still it can still take the advantage from randomization, and also it can boost the statistical power because the before-after comparison, also across the comparison, and repeat measurement. Those things can increase the statistical power. And there have been more and more articles published with such a study design, especially for the intervention of the policy change. So these are some examples with a huge scale step-wedge study design randomized control trial. Okay, so we just know it. There's something called the SWD, which is modification of randomized control trial, which is even better than a typical random control trial in terms of biostatistics. It's very feasible for policy. Okay, personal insight. The first one, most of the effect of RCT are about protecting study subjects' own good, because it's very important to think about the people's benefit. The purpose of research is to take good care of people, not to harm them, right? But still conserve its scientific framework, but still need to maintain the scientific framework, especially the randomization. And no bargains on the basic rules, especially random allocation, please. That's the spirit or the essential foundation for randomized control trial. Why it does matter? Because it could even control the confounders we don't know, or we don't have the information about it, but still could be controlled somehow because it's been randomized to do comparison groups. So it's a typical cohort study. The only difference is that we could allocate the exposure randomly. Okay, and also they have been randomized to different groups. So theoretically, the characteristic of these two intervention and placebo groups will be very similar to each other, right? And it's the most feasible study in clinical settings for unique studies because the intervention is endless. You could always find something innovative for intervention, right? Even chewing gum for the purpose of sugar control. Yeah, it could be an innovative one, right? Who knows? Or maybe it works. Read my lips. First one, RCT study design closest to generic experiment, right? Because in most of the other study design or observational study design, what we can do is just stay aside to see what's going on, right? So people just choose to expose or not, right? So the only thing we can do is that. But for randomized control trial, we could allocate them randomly into two groups, and also we could give them or manipulate their exposure. So it's closest to real experiments, but there are a lot of limitations because they are human beings, they are not rats, they are not cell line or insects. A clear protocol is essential to all RCT at the stage study design, especially for subject selection. You have to make it very clear in the protocol and follow the rule from the beginning to the end stringently. Key point, randomization is the soul of RCT, which could even control the confounders we don't know. Okay, they'll be definitely the most important thing in RCT. Intent to treat analysis. Why it does matter? Why is it important? Why is it better than the other statistical analysis methods? It's something you would better follow in methodology at the stage of data analysis. Okay, just keep people in the original groups, even if they drop in or drop out or refuse to take the intervention or placebo anymore. You have to beg them to come back to provide information for the outcome They can perform so-called intention to treat analysis. So it's not about statistical stats at all. No, I did not mention any statistical test, right? Chi-square test, the t-test, it's nothing about that. It's about the way you collect the data and the way you perform the data analysis. What you want to know is efficacy, but what you can get is just effectiveness in RCT. So please use this term to show that this is the effectiveness of the study, because it's real life, it's a real world data, it's a real world study, it's not a perfect situation happening only in the heaven. Okay. Also, I upload an article which is called Alcohol Acutely Enhanced Decoding of Positive Emotions and Emotional Concerns of Positive Stimuli and facilitate the view of sexual images. Wow, such an interesting topic, right? It's about alcohol, it's about sex. Is there anyone major in psychology for undergraduate? No? Yes? But no matter how, you take the course of psychology, right? Okay, so you should have some idea about it. Read the article and join the discussion for next week. And I have give you the discussion topic. What was the study design? Of course, randomized controlled trial, right? What was the sample size? You could find it easily in the abstract. What is the outcome of the study? It's even covered by the title, right, already. And what measurement tool were used for these outcomes? About the sexual image, about something, the psychological thing. Of course, they use the tool to do it, right? And what were the intervention and placebo? Okay, they might use the other term, but you have to know it. What is intervention? Beer, right? And what is the placebo? Something tastes like a beer, right? And what was the purpose of washout period? Okay, it's been given in the first part of my course of randomized controlled trial, remember? Okay, washout period. I'll just wait for a period of time to get rid of the effect from the intervention, right? And what were the exclusion criteria and why they need to exclude them? There's always certain reason for that. They don't do it blindly. Think about why they need to exclude those people, like a pregnant woman, why they need to exclude the ones who are pregnant. Because it's illegal or it's not ethical to random allocate them to drink beer, right? Or some have the allergy to alcohol, or someone might have alcohol drinking problem and they might not be able to join your research. Eighth, what was the major problem of statistical analysis in the first place? It's about today's lecture, right? What you're supposed to do? Baseline comparison and intention to treat analysis. Did I do it? Did I do it properly? That's the key point. Number 9, what was the other major problem in data analysis? Think about it. You've taken a course given by Andre, and we finished almost all the course in epidemiology. So you are supposed to, okay, but it might be a little bit challenging. Last one, 10 questions. How did they find the specific results for women? Okay, it's covered by today's lecture, right? So after the lecture for 3 hours for RCT, you are supposed to understand everything about this, right? Okay, so be very interesting for the discussion. Okay? Thank you. Thank you.